Welcome everyone. Today we will be talking about predicting redox reactions. So redox is that short term for reduction oxidation. And so let's get going here. The transfer of electrons between two entities, which includes atoms, ions, molecules, in a redox reaction can be thought of as a tug of war for electrons. So electrons are being pulled between these two entities. And if one reactant is able to pull electrons away from the other, a spontaneous reaction occurs. So when you think of spontaneous, you think, okay, well that's going to happen. Like they just go together and boom, happens. If not, no reaction occurs. So if no reaction occurs, I'm just going to grab a purple pen here. We're going to make a little note here. And that is called non-spontaneous. All right. So let's think of an example here for a spontaneous reaction. When you put vinegar and baking soda, the two reactants react together and you end up with byproducts. A reaction occurs. Now, a non-spontaneous reaction is, let's say you put mix two solutions together and nothing happens. They just separate. So like you could think like water and oil. That would be a non-spontaneous reaction. All right, a couple images here to take a look at. You could check those out. All right. So without mixing all possible reactants and observing any evidence of reaction, how can we predict if a reaction will occur? If a reaction occurs, what will be produced? All right. So by observing many successful as well as unsuccessful, that's a really important part. There's a lot of things in chemistry that are unsuccessful, especially reactions. Patterns emerge and empirical generalizations can be made. All right. Oxidizing and reducing agents. All right. Grab a highlighter, green. A reducing agent causes reduction by donating, losing electrons to another substance in a redox reaction. During this process, this is the key part here, the reducing agent is oxidized. All right. An oxidizing agent causes oxidation by removing, gaining electrons from another substance in a redox reaction. Switch my highlighter pen here to, let's go light blue. During this process, the oxidizing agent is reduced. All right, so you kind of have to work those backwards in your head. Whereas the reducing agent is oxidized and the oxidizing agent is reduced. What that means is that the oxidizing agent is good at encouraging oxidation. The reducing agent is really good at encouraging reduction. However, though, to do that, the reducing agent has to be oxidized. The oxidizing agent has to be reduced. So we have this reaction here. We have silver in an ionic form reacting with copper solid to produce silver solid and copper 2+ as an ion. So our ions are reduced to a metal. So ion reduced to metal, and our metal is oxidized to a metal ion. All right, so we talked about this in our last lesson, so we're just going to keep rolling on here. One of the things I want you to notice, though, is that our ions become solids and they undergo reduction, and that is our oxidizing agent. Our reducing agent is the solid, and it has to oxidize to become an ion. All right, we have this table here. I'm going to fill this in, and then we're going to look over why that is. Before I fill this in, actually, I think we're going to hop onto the next slide here just to discuss why we'll fill in the table the way we will. So let's talk about a redox table. And up until now, we have generally assumed that all single replacement reactions are spontaneous. So for instance, we could take a look at our silver nitrate, AgNO3, reacts with sodium solid. And we know that the products of this would be sodium nitrate and silver, and silver solid. All right, this would be aqueous and this would be aqueous. All right, we've always been able to assume that this reaction will happen. Our evidence from our lab has provided, though, that this is not so. So not always when we mix, try to do a single replacement reaction, are we going to have a spontaneous reaction? So how do you know when a chemical reaction will occur spontaneously without actually doing the reaction? First place we're going to start is by looking at the evidence from our lab. All right. So we have some reactivities of metal ions with metals. So let's say we did a lab here. We reacted some sodium ions, some copper ions, some lead ions, and some zinc ions with metals that include copper, lead, zinc, and silver. And what we found was that silver reacted with copper, it reacted with lead, and it reacted with zinc. So the reactions we got was 3. However, though, we reacted our copper with lead and zinc, and we only got 2 reactions. When we reacted it with the silver metal, nothing occurred. When we reacted our lead ions with the different metals, the only metal it reacted with that included silver and copper, and lead wouldn't react with itself. The only one it reacted with was zinc, so we only had 1 reaction. And then zinc didn't react with any of the metals, so it is actually the least reactive. So we have this bottom part here, reactivity order. And with that, what we see is that more reactions you have, your greater reactivity. So this correlates here. All right. So the order of reactivity is also the order of strength as oxidizing agents. All right. So oxidizing agents is sometimes written as OA. And when we look at this table here, it sorts our oxidizing agents from our strongest oxidizing agent to our weakest oxidizing agent. So our silver ions here, this is our strongest oxidizing agent. So we can call this our SRA. SRA means strongest, that's SRA. Getting ahead of myself here. So my SOA, strongest oxidizing agent, has to undergo reduction. However, though, it likes to react with it's going to greatly encourage oxidization to occur. So when we have this reaction here between Ag plus and zinc solid, this reaction, it wants to. It's a very spontaneous reaction. Whereas, tried to back up here. This reaction between Ag plus and Cu solid is not as spontaneous. So another way you might think about this is that when we go think about bonding, we can think about dipole, is that if we have sodium and fluorine, that's a very strong polar molecule. However, though, if we have chlorine bonded onto oxygen, that's not, yes, there you could say, well, the electronegativities are different. Yes. However, though, they're not largely different, so they're not as strong of a dipole. Same thing here, that the stronger our oxidizing agent and the weaker our oxidizing agent, the more spontaneous this reaction is. All right. So the order of reactivity of the 4 metals can be obtained in the same way. So before we were looking at our ions, and what we saw was that our silver ion was our strongest oxidizing agent. Our zinc 2+ would have been our WOA, which is our weakest oxidizing agent, which means that it wasn't great at causing anything to undergo oxidation, and it did not want to be reduced, or undergo reduction, I should say. All right, so we're looking at our zinc solid, our lead solid, our Cu solid, and our Ag solid. So whereas Ag plus the ion was our SOA, our strongest oxidizing agent, it's now our weakest reducing agent. All right. Zinc solid, it will react with everything. It wants to undergo oxidation. So the way it does that is it is our strongest reducing, it is our strongest reducing agent. All right. So the reactivity order, it reacts with the most entities, which means it is has the greatest reactivity. And then working our way down, Ag plus is the least reactive. All right. So we have our strongest reduction agent, which means that it wants to undergo oxidation and it causes something else to undergo reduction. A reduction agent means that it makes something want to reduce. Our oxidizing agent means it makes something want to undergo oxidation. The most reactive metal, zinc solid, has the greatest tendency to lose electrons. And if we go back to our acronym of oil rig, kind of messy R there. Oil rig, it wants to lose electrons. And lose electrons, oxidation is loss of electrons. So that zinc metal, it is our strongest reducing agent. All right, up here, this is our strongest reducing agent because it wants to undergo oxidation and lose electrons. An Ag solid shows no tendency to lose electrons in the combinations tested. So we had that table before, which showed us our strongest oxidizing agent. Similar table. We're looking at our strongest reducing agent now. All right. So we have our zinc solid. It wants to undergo oxidation, and it's happy to do that. It'll gladly do this. Our Ag solid, remember, it did not want to do this. So what this means is that Ag solid, it does not want to undergo oxidation, whereas zinc does. And what that means is that because zinc wants to undergo that oxidation, it will make something else undergo reduction. All right, I'm going to stop sharing here just so we can take a break, and then I will come back with part 2 right away.